Right, I'm going to go over an Edexcel paper from 2023. It's Physics Combined Science, Paper 2, Foundation. You get 1 hour and 10 minutes to do it, and it's worth 60 marks. Question 1. Part A. Figure 1 shows the parts of an electrical circuit. Draw the circuit diagram of this electrical circuit in the space provided. The battery symbol and some of the connecting wires have been drawn for you. Right, so the battery's over there and it comes out and goes into a switch. So it comes out and goes into a switch. I've drawn an open switch. Then it comes out and goes into a lamp. So then it comes out and goes into a lamp. Or you could draw your lamp like that. Then it comes out and goes into a resistor. Comes out, goes into a resistor, and then it just goes back to the battery. So there you are for 4 marks. Part B. Figure 2 shows the current flowing into and out of point P in part of a circuit. There's P. A little junction. Which of these is the value of current I? Right, this is Kirchhoff's law. What goes into the junction must come out. So 7 amps went in, 2 came out so far, so this must be 5 amps. The answer is B. Question C, part 1. There is a current of 0.46 amps in a lamp. So that's the current I. Calculate the total charge, so Q is our target, that flows through the lamp in 30 seconds, so that's T. I would always write down the symbols of the things you know, and then here is the equation to get the charge. So Q equals I times by T. Pop the numbers in. I was 0.46 amps and the time was 30 seconds, and that comes out as 13.8 coulombs. Part 2. The voltage across the lamp is 6 volts, that's our V. The current in the lamp is 0.46 amps, so that's I. Calculate the energy transferred, so energy is our target, to the lamp in 1 minute, so time equals 60 seconds. Your time always needs to be in seconds. Use the equation, energy equals current times by voltage times by time. So E equals I times by V times by T. Pop the numbers in. Current was 0.46 amps, the voltage was 6 volts, and the time is 60 seconds, and that comes out as 165.6 joules. Question 2, Part A. This question is about magnets and magnetism. Figure 3 shows a magnet that has picked up 3 paper clips. The poles of the lowest paper clip are labelled. Label the poles of the other 2 paper clips in figure 3. Right, well, if they're attracting, if that's a south, then this must be a north, and if that's a north, that means this end must be the south, and if that's a south and this is attracting, that must be the north, and then that must be the south. And that would attract to the north. So yeah, that's right. Part 2. Complete the sentence by choosing a word from the box to describe the type of magnetism that these paper clips have. So these paper clips have, it'll be induced because it's temporary magnetism. As soon as you take those off that magnet, these will no longer be magnetic. Part 3. Suggest a material that these paper clips in figure 3 could be made from. Well, they're most likely iron. However, they could be steel, nickel or cobalt. They're the 4 magnetic materials you need to know for GCSE. Part 4. When the paper clips were pulled off the magnet, they fell separately to the table. Describe how you could test whether any of the paper clips had kept any magnetism. Right, well I guess the easiest thing to do is to bring the paper clips back together and see if they will still attract. Another thing you could say is to put a compass next to them and see if it affects the needle. See if the needle moves. You could even say sprinkle iron filings around them and see if it creates a pattern of the magnetic field. Part B. Figure 4 shows the magnetic field around a wire carrying a current. And there we are. State how you can tell from figure 4 that the strength of the field is greater at P than at Q. So the strength of the magnetic field is determined by how close the lines are. So the lines are close together at P and they're far apart at Q. Part 2. The magnetic field strength is measured at P for different values of current in the wire. The results of this investigation are shown in figure 5. Describe the relationship between the magnetic field strength and current. Right, well as the current is getting bigger and bigger, the magnetic field also gets bigger and bigger, and it's linear because it's a straight line. Or, because it's linear and it goes through the origin, 0, 0, you can say it's directly proportional. Question 3. Figure 6 shows part of the UK national grid system for the supply of electricity to homes. Electricity supply to homes has a frequency of, right, it's 50 Hz. That's one of them, you either know it or you don't. Part B. Explain why the national grid uses high voltages with small currents to transfer electricity from power stations. Right, if you've got a small current, it means the wire won't get as hot, so you'll not be losing your energy or power as heat, and it makes it more efficient. Part C. Figure 7 shows details of a transformer. Calculate the power in the primary coil. Use the equation P equals V times by I, and it must be the primary. So what is the voltage in the primary? So this is the primary coil over here, and that's the secondary coil there. So the voltage in the primary is 12,000 volts, and the current in the primary is 0.64 amps. Multiply those together and that comes out as 7,680, and that'll be watts. Part 2. Calculate the following for the transformer in figure 7. Number of turns in the secondary coil divided by number of turns in the primary coil. Right, so the number of turns in the secondary coil is 1600, and we simply need to divide that by the number of turns in the primary coil, which is 80,000. And that comes out as 0.02. Part 3. For the transformer in figure 7, evaluate, in its simplest form, the ratio secondary voltage to primary voltage. Right. The secondary voltage is 240 volts and the primary voltage is 12,000 volts. So that was 240 volts to 12,000 volts. Now to simplify the ratio, if we do 240 divided by 240, that'll come out as 1. And whatever we do to the left hand side, we've got to do to the right hand side. So we'll do 12,000 divided by 240, and that comes out as 50. So it's a 1 to 50 ratio. Question 4. This question is about energy transfers. Figure 8 shows the apparatus used for investigating the transfer between gravitational potential energy and kinetic energy. A metal ball is attached to a thread. The ball is released from a starting position and swings on the thread. The ball cuts a light beam at the bottom of its swing. When the ball cuts the light beam, the speed of the ball is recorded by the data logger. The ball was released 3 times from the same height and the speed measured each time. The measurements of speed are given in figure 9. Part A. Calculate the mean speed. Right, we've just got to add them together and divide it by 3 because there's 3 readings. Make sure you use the brackets so that it's not just the last number that gets divided by 3. And that comes out as 1.2466 recurring. How many decimal places? I would put it to 2 because they've put all of theirs to 2. So that goes to 1.25. Part B. Suggest one reason why the measurements of speed were repeated. Well, it's to identify anomalous results, which just means any results that don't fit the pattern. You could also say it improves reliability, and that's because it might be difficult to drop it from the same height each time. You could also say it's to make it more precise. Don't say it to make it more accurate though. Question C. The mass of the ball is 0.052 kilograms, so that's M mass. The ball falls through a vertical height, delta H, of 5 centimetres. Right, let's convert that into metres. So 5 divided by 100, because there's 100 centimetres in a metre. So that'll come out as 0.05 metres. Gravitational field strength G is 10 newtons per kilogram. So that's in kilograms, so we don't need to convert anything there. Calculate the change in the gravitational potential energy of the ball. So we're looking for the change in GPE. That's our target. And use this equation. Right, so we just need to pop the numbers in. And that comes out as 0.026, and that'll be joules because it's energy. Question D. Figure 10 shows an end-on view of the ball's swing from its starting point. Part 1. To measure the change in vertical height delta H through which the ball moves, a ruler could be used. Draw a ruler on figure 10 placed in a position to measure the change in vertical height delta H. Right, so the ball's starting there and it's going down to there. So we'll need to measure the height like that. So we'd better put our ruler over there like that. Make sure you place the ruler so that it definitely covers that distance there, that vertical height. Part 2. Figure 11 shows a set square. That's this thing here, if you've never used it before. Describe how the measurement of the change in vertical height delta H could be improved using the set square. You may add to figure 10 or figure 11 to help your description. Right. Well, if you place the set square there like that, you'll make sure that the ruler is vertical because that's 90 degrees. Place the set square on the ruler at 90 degrees to make sure the ruler is vertical. Question 5, Part A. The voltage or potential difference across a length of wire is 1.5 volts, that's our V. A charge of 0.042 coulombs flows through the wire, that's our Q, the charge. Calculate the energy transferred, so E is our target. Use the equation. Right, so we can just pop the numbers straight in, don't need to rearrange it. And that comes out as 0.063 joules. Part B. Figure 12 shows some of the apparatus that students use to determine the resistance of a piece of iron wire. Add connecting wires, a voltmeter and an ammeter to complete the circuit in figure 12 so that the students can determine the resistance of the piece of iron wire. So that's the iron wire there. We'll need to connect that up. We'll need to pop an ammeter in series, which means next to the iron wire. So you could have either put it anywhere here or put your ammeter anywhere here. And a voltmeter needs to go in parallel across the iron wire. Part C. The students extend the investigation to determine how the resistance of the iron wire changes with its length. Give the name of one additional piece of apparatus the students would need. Well, they'll need a ruler. And they'd place it up there. They haven't asked you to draw that, so just say a ruler. Part 2. Figure 13 shows a graph of the results. Draw a straight line of best fit on figure 13. Right, what we got? Length along the bottom, resistance up the side. Well, if the length is 0, the resistance is going to be 0. So we know that the line of best fit has to go through 0, 0. Now the way I like to do it is just start from 0, 0 then. And if we go up to the last dot, the last data point, and we'll just see, does that make sense? Are we happy with that? I am happy with that. How do I know I'm happy with that. Well, it's gone through 1, 2, 3, 4, 5 points, and we've got roughly the same number of data points below the line as we'll have above the line. It's a 2 to 1, so that's fair enough. Part 3. Use figure 13 to estimate the resistance of a 100 centimetre length of the iron wire. Right, 100 centimetres of the length. So if I was to continue this line, trying to keep it straight, well, it looks about right. Then our value is going to be here, which is 3 ohms. They'll always allow you a range, so it depends on what your line of best fit was. They'll actually accept anything between 2.7 and 3.3. Part 4. The variable resistor shown in figure 12 is used to prevent the iron wire from becoming too hot. Explain how the variable resistor is used to prevent the iron wire from becoming too hot. Right, we use resistors to control the size of the current. So the resistor keeps the current smaller. So current would make the wire get hot or heat up. So smaller current means less heat. Part D. The potential difference or voltage across another piece of wire is 1.56 volts, so that's V. The current in the wire is 0.45 amps, that's our I. Calculate the resistance, so that's our target, R, of this piece of wire. Use the equation V equals I times by R. Right, we're going to need to rearrange this, so we can use a magic triangle, do a top shelf and a multiplied sign. Something times by something, and we've got room for something times by something, so shove that in. One space, one thing, shove that in there. Now cover up what you're looking for, so we're looking for R, cover up R, and we are left with V divided by I. So R equals V divided by I. And we'll pop the numbers in. 1.56 volts divided by 0.45 amps, and that comes out as 3.46 recurring ohms. They've used 2 decimal places for their numbers, so we'll use 2 decimal places for ours, so that'll round up to 3.47. Question 6, Part A. Which of these means changing state from solid directly to gas? That is sublimating. So sublimate or sublimation or sublimating is when you go directly from a solid directly into a gas. Part B. An object has a mass of 7.22 times 10 to the minus 2 kilograms, so that's M, and a volume of 2.69 times 10 to the minus 5 meters cubed, so that's V, volume. Calculate the density P, or rho, of the object and use the equation rho, or wiggly P, equals M over V. So we just need to pop the numbers in, we don't need to rearrange anything. And that equals 2684.0. And the units, if we are taking kilograms and dividing it by meters cubed, it is literally kilograms divided by meters cubed. Question C. Aluminium has a melting point of 660 degrees C. The absolute zero of temperature is minus 273 degrees C. Calculate the melting point of aluminium in Kelvin. Right. Well, hopefully your teachers told you. Minus 273 degrees C is equal to 0 Kelvin. So to go from 0 Kelvin back up to 0, you've got to add 273. So in other words, 0 degrees C is going to equal 273 Kelvin. So whatever degree C you've got, if you want to convert it into kelvins, you've got to add 273. So we've got 660 degrees C. We'll need to add 273 to that, and we'll get our answer in Kelvin. And that comes out as 933 Kelvin. And obviously, if you want to go from kelvins back to degrees C, you would take away 273. Part 2. Describe the motion of particles in liquid aluminium, so above 660 degrees C. But the important thing here is, what do the particles in a liquid behave? Well, their motion would be random, and we're not looking for the arrangement, we're looking for the motion. Some of the particles would move fast and some of them would move slow, so we've got various speeds or velocities or kinetic energy. They'd be bumping into each other. That's the particles. And they'd move faster than they did when they were a solid. You could even see the particles slide over each other. Any two of that. And finally, question D, our 6-mark question. The table shows some properties of two materials used as thermal insulation. The higher the R value, the better thermal insulating properties of the material. So high R equals better insulator. Assess which of these materials may be the more suitable to use as a thermal insulation in a building. Your answer should compare the properties of fiberglass and polystyrene given in the table. Right, so we've got fiberglass. It says it's made from sand. We've got the R value, which is lower than polystyrene's R value, which is made from petrol. The fiberglass is non-flammable, so that's good, whereas the polystyrene melts at 270 degrees C and spreads fire very quickly. Right, let's start by talking about fiberglass. So it's got a lower R value. Right, so what does that mean? It means it's going to be a worse insulator. So what you should be doing is you should be looking at the value, but you should also be putting an interpretation on it to say what that means. Now, fiberglass have got dangerous particles that you can breathe in. Now, it's made from sand, which is readily available, so that should make it cheap. Plentiful supply. And a really good thing is it's non-flammable. Now don't just say non-flammable though. Well done for being able to read, but what does that mean? It means it's safer than polystyrene. So 1, 2, 3, 4, 5, 6, 7. So we've said 6 things. Now let's say some stuff about polystyrene just in case. So it's got a higher R value, so it's a better insulator than fiberglass. Now it's made from petroleum oil, so it's made from oil which is running out. Now that could make it expensive, because it would have to be extracted, and that could make it environmentally damaging to the environment. And it's dangerous because it spreads fire very quickly and it melts. You'll have all sorts of toxic fumes coming off it if it's oil. Right, we've put loads of stuff there. You'll definitely get 6 marks. I think the important thing to realise is don't just quote the data, quote it and then say what that means and compare it to the other one. Right, well I hope that's been useful for you. The more of these you do, the better you'll get. I'm telling you, your grades will go right up the more of these you practice. So well done for investing time in your personal development. Work hard, be nice, and see you in the next video.
Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained.